Good evening, everyone. Myself, I'm Faaiz. I'm from AIIMS Nagpur. So, yeah, our topic of discussion is, today we are discussing about capacitance, then capacitors and dielectric. Okay, let's directly get into action. Okay, first, let's discuss about what is parallel plate capacitor. Okay, parallel plate capacitor. Parallel plate capacitor. See, okay, this is actually parallel plate capacitor. Okay, so the electric field here is, we all know, because of C plus Q charge minus Q charge. Okay, if I'm taking at point A, electric field at A will be due to plus charge sigma by 2 epsilon, and due to negative charge negative Q sigma by 2 epsilon. Right. That will be, both will be in same direction. So the net electric field will be sigma by epsilon. Okay. If these two plates are separated by distance d, and we know that potential difference will be ED. Okay. So potential difference will be, what is electric field of sigma by epsilon into d. And we know that C is equal to Q by V. That is, capacitance C is equal to Q on sigma d into epsilon. And what is Q in terms of sigma? What is sigma in terms of Q? Q by A. So Q epsilon by, sigma is Q by A. Surface charge density, right? Q by A into D. QQ. We can cut Q. So this will be the capacitance of a parallel plate capacitor. C is equal to A epsilon by D. Okay. Suppose if vacuum is present in between the plates, what if a dielectric which has constant K, dielectric constant K, then capacitance will be just multiply with K, K A epsilon by D. As simple as that. Okay, no doubt. Easy. Okay. Next is energy stored in a capacitor. Okay. Energy stored in a capacitor. Again, energy stored in capacitor formula before that. We know that energy, the volume is, energy density is, that's volume is half epsilon E square. Okay. And is volume here A into D. Parallel plate capacitor, no? Parallel plate capacitor. So area is A and distance between the is D. So volume will be AD. So energy will be half epsilon E square AD. So this will be the total energy. This will be the total energy. Okay. Then by putting C is equal to A epsilon by D, that equation, we will get energy is equal to half CV square. And again, we all know that Q equal to CB. Then again, we will get half QV, Q square upon 2. Okay. These are the formulas for total energy. Okay. Half CV square, half QV, Q square by 2Z, and half epsilon E square A. Easy. This is our first question. Let's read the question. A parallel plate capacitor with plates of area 1 meter square each. So area is given. Area is 1 meter square. R separation D is given 0.1 meter. If the electric field between the plates is, electric field between the plates is given 100 Newton per coulomb, the magnitude of charge on each plate. We have to find out the magnitude of charge on each plate. We know that the electric field, between parallel plate capacitor is sigma by epsilon. Okay. Sigma is surface charge density. We can write Q by A. This will become Q upon A epsilon. We have to find out charge, right? Q is equal to electric field into area into epsilon. What is electric field here? 100, 10 raised to 2. Area is okay, area is given 1 meter square. That is 1 into, what is epsilon? Yeah, epsilon is 8.85 into 10 raised to minus 12. Yeah, we all know that. So let's solve this problem. So 8.85 into 10 raised to minus 10, right? So option C. Option C is the right answer. Yeah, very easy question, right? Yeah. Next we can talk about dielectric. What if? See, parallel plate capacitor separated by distance d, area of each plate is A. Suppose vacuum present in between plates, then capacitance is A epsilon upon D. Easy, no doubt. Okay, here see, I inserted a dielectric having dielectric constant K. Okay, then capacitance will be K times A epsilon upon D. Easy. Yeah. Next, two more formulas. See, electric field here will also change. Yeah, electric field become, net electric field inside dielectric will be electric field present in the vacuum divided by K. Just divided by K. Okay. Next is C. Okay. So if it is plus Q, then here it is minus Q. Then charge will redistribute, right? 0. Then here plus. Here it will be minus. So if I place a dielectric in between them, in charge will redistribute, right? Inside electrics. How? Like this. Minus will come this side, negative charge will come this side, and positive charge will come this side. Yeah. Where are we? Yeah, E net is equal to E vacuum divided by K. Okay. And then, surface charge. That charge, charge density induced on the electric will be, sigma into 1 minus 1 by K. Again, charge induced is also Q into multiply with 1 minus 1 by. Easy. These are just formulas just by heart. Okay. So E net is equal to E vacuum divided by K, and surface charge density induced on electric is sigma into 1 minus 1 by K, and the charge induced is equal to Q into 1 minus 1 by K. Easy. Yeah, so E net is equal to E vacuum by K. Surface charge density induced is equal to sigma into 1 minus 1 by K. Charge is equal to charge into 1 minus 1 by K. If I place a dielectric having dielectric constant in between the plates. Easy. Yeah. Let's get into our question. See, a parallel plate capacitor is made of two circular plates separated by distance 5 millimeter. Distance is given, and with a dielectric constant K is given. When the electric field in the dielectric is 3 into 10 raised to 4, the charge density of the positive plate will be close to. So it's given electric field in the dielectric. We know that electric field in the dielectric, that is E net is equal to, if no been formula, E vacuum divided by K. What is E vacuum? Sigma by epsilon. So in electric field inside electric will be sigma by K epsilon. Easy, no doubt. That is given in question. Sigma by K epsilon is how much? 3 into 10 raised to 4. It is given. We have to find out charge density. So we have to find out sigma only. Sigma is 3 into 10 raised to 4 into K into epsilon. Okay, what is K? K is given in question, that is K is equal to 2 point. And epsilon we know 8.85 into 10 raised to minus 2 here. Let's solve this question. So 3 into 2.2, how much? 3 into 2.2 will be 6.6. 6.6 into 8.8 into 10 raised to minus 8. Yeah, approx will be 7 into 9. Yeah, 7 into 9 will be so 56. Okay. 7 into 9, how much? 7 into 9, 63, right? So like 63. 63 into 10 raised to 8. Almost 6.3 into 10 raised to minus 7. So almost raised to minus 7 and 6 something like. So yeah, option suiting with this is 6 into 10 raised to minus. Option A is the answer. Easy. Yes. Next question. It's a very easy question. A uniform electric field E exists between the plates of a charged condenser. A charged particle enters the space between the plates and perpendicular to electric field. The path of the particle between the plates is very simple question. See, this is the picture. This is a picture we will get. Yeah. Okay. So electric field exists from right. This is the direction of electric field. Okay. Yes. Electric field here. What charge a particle? No, a charged particle enters. Suppose Q, charged particle enters with velocity V. Charged particle enters, not okay. So it is having some velocity. So you have to find out the path of the particle. Simple. We know. Yeah. Y direction. S is equal to ut plus half a t square. Y is equal to uy t plus half a y t square. Here Ay is 0. There is no force in y direction. Okay. Okay. Because this is massless, right? Charged particle. Just charged particle only. So gravity doesn't matter here. So y is equal to simply v into t. That's all. But in x direction, x displacement will be ux is 0, but we have ax. Ax will be because of this electric field E. Yeah, there is a force that is Q E. Q into E, charge into electric field. So x rest be divided by mass. So Q E by M half t square. Right. So x is equal to, and we got an equation t is equal to y by v. T is equal to y by v. So half into q e by m t square, that is y square upon v square. So actually x is proportional to y square. Yeah. Which curve corresponds to this equation? Yeah. X is proportional to y square. Of course, it is parabola. Option C is our answer. Easy. Yes. Yeah. Next discuss about the charge distribution. And very simple. What? See, I have a capacitor, so I connected to a battery. Yeah. Easy. Voltage V, capacitance C. Okay. So Q is equal to CV, we all know, and V is equal to Q by C. Right. So work done by battery will be how much? Work done by battery will be C. Work done by battery will be charge into potential difference. Right. Charge is CV. Q is equal to CV. CV into V. That is CV square. And we know energy stored inside a capacitor is we already half CV square. So energy stored inside a capacitor is half CV square. So see, work done by battery CV square. Energy stored inside the capacitor is half CV square. So remaining amount of energy, that is half CV square, is lost somewhere. That is lost as a form of heat. So here heat loss is equal to again half CV square. That is CV square minus half is CV square. That is CV square. Okay, easy. Yes. Next, see. Okay, I have a capacitor having capacitance C1 plus minus voltage V1. Okay, another C2 plus minus V2. Okay, yeah. I connected parallelly. Okay, these capacitors. So this is the final picture I have. Okay, connected plus to plus. Okay, plus to plus, minus to minus. So C1, yeah. So what will happen if I connect? Yeah, charge will redistribute such a way that both will have same potential. Yeah, because I am connecting parallelly C to V. Right. So both will have, yeah, Q1. This is will be Q2. Easy. So the final potential, yeah, the final potential will be that common potential. V final will be C1 V1 plus C2 V2 upon C1 plus C2. And charge Q1, yeah, charge flowing through capacitor 1 will be C1 upon C1 plus C2 into charge total, and charge flowing through capacitor. Second capacitor will be C2 divided by C1 plus C2 into Q. Easy, simple formulas, okay. Yeah, V final is equal to C1 V1 plus C2 V2 divided by C1 C2, C1 plus C2. And Q1 is C1 by C1 plus C2 into Q total. Q2 will be C2 by C1 plus C2 into Q total. Easy, yeah, just formulas only. Yeah, and the very important formula. So during this process, okay, during this process, the energy loss, the heat loss is equal to, during this process, heat loss is equal to half C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. Half C1 C2 by C1 plus C2 into V1 minus V2 whole square. Easy, yes. Yeah. This is the first question. A capacitor C is fully charged. A capacitor C is fully charged with voltage V0. After disconnecting the voltage source, it is connected in parallel with another uncharged capacitor of capacitance C by 2. Energy loss in the process. Simple energy loss, we have equation half C1 C2 upon C1 plus C2 into V1 minus V2 square. Okay, here what is C1? C1 is C. V1 is V0 and C2 is C by 2. V2 uncharged, that means voltage V2 is 0. Just, okay, half into, I just insert those values. Half into C1 is C, C2 is C by 2, C1 plus C2 will be 3, 3C by 2 into V1, V2 is 0, so V0 square. How much? This will be half into C, 1 C will, we can cut, yeah, half we can cut, 1 C by 3 V0 square. Actually, 1 by 6 CV0 square. 1 by 6 CV0 square. Option will be, option D is correct answer. Easy. Simple application of formula. Simple application of formula. Right. Yes. Next question. What is next question? In the figure shown, after the switch S is turned from position A to B, energy dissipated in the circuit in terms of capacitance C and total charge Q. Again, very simple, yeah, simple application of our formula only. What's the formula? Half C1 C2 upon C1 plus C2 into half C1 C2 upon C1 plus C2 into V1 minus V2 whole square. So see, first, yeah, C1 C2 upon C1 plus C2 into V1 minus V2 whole square. So see, first, C1 C2 upon C1 plus C2 into V1 minus V2 whole square. So see, first, C1 C2 upon C1 plus C2 into V1 minus V2 whole square. So see, first, Yeah, C1 is C, C2 is 3C. What will be the V1? V1 will be, see, this is connected, first. So V1 will be Q by Q is equal to C. Yes. So yeah, V1 will be how much? Q by C. Or yeah, in first condition it will be like Q is equal to C. That's all. C. So V2 will be 0. V2 will be 0. V1 is E only. Yeah, it's connected with E. So formula heat loss equal to dissipated, that is heat loss only. Half into C1 C2. Half into C1 C2. C into 3C upon C1 plus C2. That means 4C. Right? Sorry, E. V2 is 0. So square. Half into 3C upon 4 square. That is, it is 3 by 8 CE square. Okay. So we have to just, we know that Q equal to CE. So E equal to Q by C. So 3 by 8 C into Q square upon C square. That will be 3 by 8 Q square by C. Yeah. Option B is the correct answer. Option B. Okay. Yeah. Next question. Two capacitors. Two capacitors of capacitance C and 2 are charged to potential difference V and 2V respectively. Okay. CV, 2C, 2V. These are then connected in parallel in such a manner that the positive terminal of one is connected to the negative terminal. Okay. Yeah. This is our equation. V final is equal to C1 V1 plus C2 V2 by C1 plus C2. If both the capacitors are connected in a way that positive plate, yeah, is touching with other positive plate. So in this question, here see, here positive terminal of one is connected to the negative terminal. So yeah, C1 V1 minus C2 V2. That's the difference. Final energy of this configuration. Again, very simple question. See, yeah, you can just find out what will be the final potential right before that. C1 is C, V1 is V, C2 is 2C, and V2 is minus 2V. Either we can take minus 2V in the plus equation, or we can just put 2V in if we make the minus. Okay. So V final will be C1 V1 plus, okay, C2 V2 upon C1 plus C2. Right. Oh, what is C1 CV plus C2 2C into minus 2V. Right. Better than that, just it will create, right. So first I am writing C2 V2. So 2C into 2V. Okay. Minus, wait, 2V, yeah, minus CV upon 3C. How much? 4CV. 3CV upon 3C. Is 4CV minus CV. That is 3CV, right? 3CV, yeah. V, yeah. Final potential is V. So V final is V. We have to find out the final energy of the configuration. So yeah, final energy of capacitor C will be half CV square. And final energy of capacitor 2C will be how much? Half 2CV square. So half CV square plus CV square is 3 by 2 CV square. 3 by 2 CV square, option B is correct. Easy? Yes. Yeah. Next question. A 5 microfarad capacitor is charged fully by 220 volt supply. It is then disconnected from the supply and is connected in series to another uncharged 2.5 microfarad capacitor. If the energy change means again what? A heat loss. Yeah. Heat loss formula. What is heat loss formula? Equal to half C1 C2 upon C1 plus C2 V1 minus V2 whole square. Here C1 is 5. Yeah, 5 microfarad. And V1 is 220. And C2 is how much? C2 is how much? 2.5. And V2 is 0 because that is uncharged. Okay, just apply half into C1 5 into 2.5 divided by 7.5 into 20 into 220, right? So 7.5, 2.5, 3, 5 by 3. That means 5 by 6. 5 by 6 into 220 into 220. 5 by 6 is okay. It's microfarad, no? 10 raised to minus 6, 10 raised to minus 6. So what will happen? 5 by 6 into, okay, wait, before that we can cut 6, no? 3, 1, 1, 0. 5 by 3 into 0.1 into 0.2. Okay, 10 raised to minus 6, 10 raised to plus 6. Katham. Sorry, Katham. So it will be 0.1 to 0.2, that is 0.02. Yes, 0.2 into 5 by 3. That means 5 by 3 into 2 by 100. That means 10 by 3 by 100. Right? That means actually 3.33 divided by 100. Yeah, so our answer will be 3.33. Right? Yes. Next question. A 5 microfarad capacitor is charged fully. Oh, this question is our next question. A 10 microfarad capacitor is fully charged to a potential difference of 50 volt. Again, simple only 10 microfarad, 50 volt. After removing the source voltage, it is connected to an uncharged capacitor in parallel. Okay, uncharged capacitor in parallel, capacitance is not given, but voltage will be 0. It's uncharged. Now the potential difference across them becomes 2. That is, finally the potential become 20 volt. The capacitance of the second capacitor is, we have to find out to C. And we know that V will equal to C1 V1 plus C2 V2 upon what? C1 by C2. No, C1 V1 plus C2 V2 by C1 plus C2. So just insert those values. C1 is 10, 50, C2, that this whole term will become 0 by 10 plus C. And final potential is given in the question, that is 20. So 20 into 10 plus C become 500. Yeah, 10 plus C become 25. That is, C become 15 microfarad. C become 15 microfarad. Easy? Yes. Is the correct answer. Next, again, a very simple topic: force between the plates. C. Okay, plus, minus. They will distribute, no, 0, 0. Yes, force will be what? Force is equal to Q into field due to one plate over another, right? Q into field due to one plate over another. Yeah, So what will be that? F is equal to Q into sigma by 2 epsilon, right? Because of one plate, right? And we know that Q is equal to sigma A, right? We know that. But sigma equal to Q by A and Q is equal to sigma A. Okay. So applying that sigma A into sigma upon 2 epsilon. So force is equal to sigma square A upon 2 epsilon. That is the formula. Sigma square A upon 2 epsilon. But if they ask pressure is equal to force upon area, that will become sigma square upon 2 epsilon. Easy. Yeah. Next, over what? Series combination. What if I connect capacitors in series? Yeah, series combination, right? Okay. C1, C2, C3. Yeah. We know that. Yeah, 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3. As easy as that. Okay. And C1, C2, C3. Same charge Q will flow through three capacitors, but potential difference across capacitors will be different. Total potential difference will be V1 plus V2 plus V3, but same charge will flow. So this will be the 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. This will be the formula. Yeah, in parallel combination, again very simple. In parallel combination, C1, C2, C3. Yeah, C equivalent equal to C1 plus C2 plus C3. Yeah, yeah. Everyone knows this equation. C1 plus C2 plus C3. Yeah. And the charge through each capacitor will be different, but potential across capacitor will be same. There will be V. Easy. Okay. Yes. Yeah. Let's directly get into question. This question, next question. Yeah. Effective capacitance of parallel combination of two capacitors C1 and C2 is 10 microfarad. It's given, okay. Parallel combination of two capacitors, okay. Okay, C1, C2, yeah, it's combined. Effective capacitance is 10 raised to microfarad. When these capacitors are individually connected to a voltage source of 1 volt. 1 volt, yeah, we connected with 1 volt. C1 also, C2 also. So C1 is C2. Okay, C1, C2. 1 volt, 1 volt. The energy stored in capacitor of C2 is 4 times that of C1. And if these capacitors are connected in series, their effective capacitance, first we have to find out C1 and C2. As simple as that. Okay, this is first parallel connection. No? Parallel connection C1 plus C2 is given 10. As easy as that. Okay, energy stored. U2 will be half C2 V square is 1 square. That is 1 only, half C2. 1 volt, right? 1 volt. And U1 will be half C1. It is given that energy stored in capacitor C2, U2 is 4 times that of U1. So C2 by 2 is equal to 4 into C1 upon 2. So 2 to C2 equal to 4C1. C2 equal to 4C1. Yeah. So from this equation, so C1 plus C2 is 4C1. 4C1 equal to 10. That is C1 equal to 2. So C2 will be 8. Okay. And if they're connected in series, 2 and 8 in series, how much? 1 by C equivalent equal to 1 by 2 plus 1 by 8. How much? Equal to 10 upon 60. or C equivalent will be 16 upon 10, that is 1.6 microfarad. So option C is the correct answer. Easy question. Yeah. Next question. In the circuit shown in the figure, the total charge is 750 microcoulomb and the voltage across capacitor C2. Across capacitor C2 is 20 volt, then the charge on capacitor C2 is. Again, a very simple question. Okay. Yeah, connected. Okay. V voltage is here. Right. So what is given? Total charge is given 750. So total charge is given, and the capacitor. Voltage across capacitor. First total charge is given how much? 750. And voltage across capacitor C2. C2 is this, no? This is C2. Voltage across capacitor C2 is 20 volt. Yeah, here capacitance is 8, right? Here also 20 volt. And its capacitance is C3's capacitance is 8. So very simple, no? Yeah. How much? So this is Q2, this is Q3, this is Q1. Q1 will be 750 only. So Q3 will be C3 into V, right? C3 is how much? 8 into V20, that is 160. So 160 will flow through Q3. So remaining 750 minus 160 will flow through Q2, right? Easy, right? Yeah. So how much Q2 will be? Q2 will be 650, 660, 650, right? With 750 minus 160. How much? 590, right? 590 plus 160. 0, 7, 0, 5. Yeah, 750. So 590 cents. Right. Option B is the right answer. Okay. Yes. Next question. Next question. In the given circuit, the charge on parallel. So that will turn as how much? 6. So 4, 4, 6. 4 and 6 are in C. So the total, see, the effective capacitance of the circuit is 5.4. Right, 5.4. So 10 volt, 5.4 microfarad. So charge will be Q is equal to CB24 microcoulomb will be the total charge. So total charge we got how much? Total charge is equal to 54. Total charge is 54. We have to find out charge on 4 microfarad. Okay, see, across 3 microfarad, what will be the potential? 10 volt. So charge will be how much? Q3 means charge flowing through Q through 3 microfarad will be C into V. That is 3 into 10. That is 30 microcoulomb. So 30 will flow this direction. So the rest 24 will flow through. Yeah, this above line. So across 4 microfarad, how much charge will flow? Easy, 24 microcoulomb. Easy question, right? Yes. So answer is option D. Okay. Next. This is a little bit tricky. Still, we can solve very easily. See, first we have two mark points. See, this is A, this is B, already given. Suppose if this is B and this is also B, right? And this is also, see, here I'm marking D, okay? And here I'm marking E. Okay. If this is E, then this is also E. Okay. This is B and this is also B. Right. This point we have to mark. This point A, C. This point is C. Easy. Okay. Find C if the effective capacitance of the whole circuit is to be 0.5 microfarad. Simple as. Okay, C. These three, one, C, two are in series, right? So this will turn out as 2 into 2 upon 2 plus 2. That is 1. Okay, 1 and 1 are in parallel. So total become 2. This total become 2. And 2 and 2 are in series. Again, this total become 1. Okay, here 2 and 2 are in parallel. So become 4, right? 4 and 2 are in series. 4 into 2 upon 6. 4 into 2 upon 6. 4 into 2 upon 6 means 4 into 2 upon 6, 8 by 6, 4 by 3. So 4 by 3 and 1 in parallel. So become 4 by 3 into 1 upon 4 by 3 plus 1. That is 4 by 3 upon 7 by 3. Right? 4 by 7. So this is C. This is 4 by 7. So it's effective. It's given as 0.5. That is 1 by 2. So 1 by 2. Will be 1 by C plus 1 by 4 upon 7. That is 7 by 4. That is 4 plus 7C upon 4C equal to 2. That is 8C equal C is the right answer. Yeah. This is again a very simple question. Yeah, but the question is very lengthy. But the concept is a very simple question. 7 capacitors, each of capacitance 2. Each of capacitance 2 connected in configuration to obtain an effective capacitance of 6 by 13. Which of the combination one figure below will achieve? That is described. Right? Yeah, let's solve it. See, 1, 2, 3, 4, 5. 5 C's are in parallel. So 5 into 2, 10. Okay, 10, right? Then 10, 2, 2 are in series. 2 in series means 1. 10 in one series, 10 by 11. No. So this option is cut. Here, for 8, 8, 2, 2, 2. Right? 2, 2 in series, 1. 1, 2 in series, 1 into 2 by 3. That is 2 by 3. 2 by 3 into 8 upon 8 plus 2 by 3. It is 16 by 3 upon 11, 13, 13 by 16 by 13. No, cut. Here see 6, 2, 2, 2, 2. 2 into 2, 1. 2 into 2, 1. 1 into 1, 1 by 2. Okay, 6 and 1 by 2. 6 into 1 by 2 upon 6 plus 1 by 2. 6 by 2 upon 12, 13 by 2. Yeah, 6 by 30. So, yeah, option B is the correct answer. Easy. This is the next question. A parallel plate capacitor with air between the plates has capacitance of 9. Okay. So 9 is equal to A epsilon by D. No dielectric. The space between the plates is now filled with two dielectric. Yeah, two dielectric. Yeah, two dielectric, right? Two dielectric. One of the dielectric has a dielectric constant K1, thickness D by 3, while the other one has dielectric K26 and thickness 2D by 3. Capacitance of the capacitors now. Simply see. First dielectric having K1 and thickness d by 3. Here K2 thickness 2d by 3. So see, it's actually series connection, right? Series connection. It is in series connection. See, okay. So first capacitance C1 will be A epsilon. A is same, no? A is same. A is same for both capacitors. A epsilon into K is K1. K1 is 3. K1 is 3. Upon D is D by 3. So D into 3. Okay. C2 will be A epsilon into K2. That is 6 upon 2D by 3. That is into 3. Right. C1 will be 9A epsilon by D. And C2 will be again same 9A epsilon upon D. So these both are in series. So if C and C are in series, then C square upon 2C, that is C by 2 is the effective. So so effective will be C effective will be 9 by right. Option C is the right answer. Okay, let's get into next question. A parallel plate capacitor having separation between the plates D, plate area A, and the material with the direct constant K has a capacitance C0. Yeah, initial condition C0. So C0 is C0 is a parallel plate capacitor having a separation between the plates D with area A and with okay C0 is A epsilon K upon D. Now, one third of the material is replaced by another material with the dielectric constant 2K. So that effectively there are two capacitors, one with area 1 by 3A. Okay. This area wise there. So this will be actually parallel connection, right? See, yeah, we can make a diagram. See, 1 by 3 they replaced, no? 1 by 3 okay. So this will be how much? 2K, right? 2 by 3 A epsilon K upon D. And C2 will be 2A by 3. 2A by 3 into epsilon into K upon D. How much? 2 by 3. Yeah, 2 by 3 A epsilon K upon D. Now we know that A epsilon K upon D is C0. So C1, C2 both are 2 by 3 C0. 2 by 3 is capacitance. So that is C. C is 4 by 3 C0. You have to find out C upon C0, that is 4 by 3. Yeah, option B is the correct answer. Right. Yeah. Let's move on to next question. This is our next question. See, a parallel plate of area 6 centimeters square and the separation is 3. Yeah, A is given, D is given. The gap is filled with 3 dielectric material of equal thickness. Equal thickness. So yeah, they are area wise. Area wise means parallel, right? So C1 will be A epsilon C. So A by 3 epsilon A1 divided by D. D is same for 3 capacitor. And C2 will be by 3 epsilon K2 upon D. C3 will be by 3 because D is same for everyone. Yeah, just A by 3. Yeah, their area wise A by 3, A by 3. So this will be what? Parallel connection, right? So just C effective. Final C will be C1 plus C2 plus C3 because they are in parallel connection. So A epsilon upon D are common. K1 by 3 plus K2 by 3 plus K3 by this will be the final calculation. But you have to find out. We have to find out. We have to find out what fully inserted in. So, okay, we have to find out the effective or dielectric effective. Okay, yeah. So A epsilon by D into K effective, which is equal to, you have to equate with this epsilon by D into by 3 we can K1 plus K2 plus K3. So can cut right answer. Okay. So yeah, I left one question. See, let's solve this question. It's a little bit tricky. See, okay, but still an easy one. See, one, two, three, five plates. Five plates. B and connected A is connected B. See, so this is not B. This is a D. Let's name as D. C. C. So no, wrong diagram. These and these are connected. See, this is C. Okay. This is C. This is C. This B, A, C, A. So how much pair we have here? Plates ka pair. Yeah, plates pair. C and B, 1. B and A, 2. A and C, 3. Right. So we are having how much pair? 5. C, B, A, C, A. Yeah, we are having 4 pairs, right? BC pair, AB pair, AC pair, then last again AC pair, right? Okay, so let's solve this. Okay, see. So if this is A and this is B, okay, between and this is D. Between A and D, between A and D, between between A and C, this is C. Between A and C, AC, AC. Yeah, they are in parallel, right? AC, AC. They are in parallel. Okay, yeah. And between C and B, BC, right? Yeah, which is in series. Okay, and between A and B, between A and B, we're having one. Okay, so CC parallel 2C, 2C, 2C by 3, 2C by 3 plus C. So turns out as 5C by 3. 5C by 3 is the C effective. And C we know what? A epsilon by T. Okay. So C effective is equal to 5 by 3 A epsilon by T. So option C is the right answer. Okay. Yeah. So everything, I think I have covered almost everything. Yes. Yeah. Then yeah. Force between plates is equal to sigma square into A upon 2 epsilon. Series combination 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So yeah, covered everything. So thank you everyone.